Alright, hi everybody, this is Mr. Nolan. This is part 2 of Fluxes. What we want to be able to do this time is to talk about how do we graph fluxes. How are we supposed to graph this? So in the previous video, we just looked at, we looked at carbon pools, and we looked at an example with forests, and we kind of looked at how to sort of tie that to the carbon cycle, and how carbon flows through an ecosystem. That's what flux means. But what we also want to be able to do is to graph fluxes. Now, this is actually easier than it might seem at first. And so as you watch this video, you can pause, you can stop, you can rewind. That's the great thing about, the magic of video, is that you can stop anytime that you want. It's not the math that's confusing, it's the logic. So one thing I kind of want to point out is about fluxes is that the logic of fluxes is more important than the math. The math is kind of a small detail. The math helps you to understand and describe how the fluxes behave. However, you can understand the logic of fluxes and understand them without getting any of the math, but you can get the math and not get the fluxes, and not understand the logic of the fluxes. And for that reason, logic is more important than math. So keep that in mind. But there's these 5 steps that we want to use if we're going to actually figure out how do we graph fluxes. The first one is that we have to identify and graph the starting size of each pool. So we're going to try to actually graph these pools changing sizes. So we have to start by knowing what is the size of each pool. You ought to be given that. I'm not going to ask you to figure that out for yourself. You're going to be given that number. You have to identify your fluxes. Identify your fluxes. Are they organic or are they inorganic? Which ones are they? So you have to figure out what they are. Calculate your net fluxes for each pool. So you have to figure out what is the net flux for each pool. Calculate the change of each pool's size, right? The change of each pool's size. And then you just have to graph the new size of each pool. Now, there's really not a lot of complicated stuff going on here. We're going to run through a couple of examples just in order to kind of give you the idea. Again, please stop at any moment that you feel like you're confused. Pause the video, stop it, rewind, go back, grab a piece of paper, try to draw these on your own. That way you can kind of get a sense for how are we supposed to do these. So let's go ahead and look at a really simple example. So in this simple example, including the ones that we're going to look at later, we have multiple fluxes going on. We have positive fluxes, we have negative fluxes, and also our flux depends on whether you're looking at the inorganic or the organic carbon. So our carbon pools are going to change over time, and we're going to be looking at a simple example in which the fluxes are balanced. So what that means is we have the same amount coming in as what is coming out. So in our example that we're going to try to graph is our first scenario. This is also in your packet, which I've included a link in the description to this video. But we're going to make a prediction. How will these pools change over the course of a couple of years? So in this particular example, we have an inorganic carbon pool, so this is the atmosphere, and this starts at 800, let's just say pounds. Let's just kind of keep things simple and say pounds. It's 800 pounds of carbon in that area of atmosphere. And our organic has got 400 pounds. So we've got these 2 pools, inorganic atmosphere and then organic. So this would be like, let's say forest. This would be a forest. So in our ecosystem, 800 and 400, and we have photosynthesis that's happening. And when that happens, our organic carbon pool, our plants, are pulling carbon from the atmosphere, inorganic carbon dioxide, and that is showing up in things like sugar, glucose, fats, proteins, that sort of thing. So those carbons are showing up in these molecules in plants. But don't forget that plants are doing respiration as well. So let's say that in this, this ecosystem, whatever this is, plants and animals, they're also producing carbon dioxide. And so we actually have if you just looked at this in terms of the plants, the organic matter, you have a positive flux. We're pumping carbons in. We also have a negative flux. We're pumping carbons out. So first, let's just think about this from one side or the other. So let's start off just by considering this from the perspective of organic carbon. So let's just kind of do some calculations here. So we're starting with 400 pounds of carbon. And there's flux going on. We have a positive flux, which is happening over here. And then we have a negative flux, which is happening down here. So we've got a positive flux and we have a negative flux. Our positive flux is 200 pounds of carbon a year, and our negative flux is 200 pounds per year. So we are gaining 200 pounds, and we're also losing 200 pounds, as long as you consider that from the perspective of the organic carbon. So think about this, how this is going to work. So I'm going to go ahead and jump ahead to the next slide, and we're going to start thinking about how should we graph this. We can start off just by thinking of the organic carbon. How should we graph this? So if we were to look at a graph like this, we have our little key here. We can see that our organic is a circle. And it started, according to the previous slide, at 400 pounds. So we've got our 400 pounds of carbon over here for our organic. And so we're going to go ahead and, for the start here, we're going to go ahead and draw a little circle for 400 because our organics are a circle. And if we jump back here, and if we look at the inorganic, that actually starts at 800. And so that would end up starting over here. And then if we were to go ahead and add up our total, we would find that 400 plus 800 equals 1200. And so we're going to go ahead and we're going to draw our total right there. So now what we said was that our organic is going to gain 200 pounds of carbon, and it's going to lose 200 pounds of carbon. So what I'm doing right now is I'm taking my fluxes that I have given to you, and we're going to add them up. If you add those up, you get a 0. This 0 is your net flux. Okay, so our change in this pool is 0. So what happens when I add 400 and 0? Well, at the end of that year, we're going to have the same amount that we started with, because 400 plus 0 equals 400. We're going to end with the same amount that we started with. Now, of course, assuming that this happens over the course of several years, if the fluxes stay the same, we're going to have, again, 400, because 400 plus a flux of 0 equals 400. So that's not very complicated. Let's look at our inorganic carbon. That is also, we look at that, that is also going to gain, it's going to lose 200, but it's also going to gain 200. And the reason why is because I told you that at the beginning, the previous slide. So if we go ahead and if we add those up, we're going to get 0, which means that, again, is our net flux. So if we take our 800, which is what we're starting with, and if you add 0, you get, guess what? 800. And so we really have no change. We have 800 again. And then assuming again that our flux stays the same over the course of the next year, 800 plus 0 equals 800. So we're going to get 800 again. And then something interesting pops up when you start looking at these totals. Something sort of interesting happens. What we find is that no matter what, every time that you add up the inorganic and the organic carbons, you end up with the same amount total. You're always going to get 1200, and that's because Earth is a closed system, and even though you're going to add carbon between pools, the total amount of carbon on Earth is going to stay the same. So this is a simple example. This is if your fluxes are all balanced, you're adding and subtracting the same amount from each of these at the same time. And something to keep in mind is that the circle and the square each represent a different pool. So I have carbon moving back and forth between these pools over the course of these several years, but the carbon is moving back and forth at the same rate. So that's why they stay the same, right? There's carbon moving, it's just staying at the same rate. So let's look at one that's a little bit more complicated. So let's look at what happens when the seasons change. You have summer and winter, we've got our seasons changing. How is this going to affect our fluxes? So let's kind of think about that. So in this example, our starting positions have already sort of been indicated here. So what we have going on is we have our organic carbon, which is starting at 400 pounds again, our inorganic, which is starting at 800, and our total, which of course is indicated at 1200. And this is at the end of the winter, and this is the very beginning of things. So these are our masses at the end of the winter, and now we're going to move into summer. So we're going to look at how things change during the summer. So if we kind of look at these pictures and think about this a little bit, you can make a prediction. Do you think that in the course of the summer, when we have photosynthesis going on, is this a forest going to get heavier or lighter? Is it going to have a positive net flux or a negative net flux? And then the same question for this forest during the winter. During the winter, is it going to have a overall positive net flux or a negative net flux? So we can start thinking about how are we supposed to graph this. Well, first you need some data. So we already have our starting masses, but we really don't know what the fluxes are. So I have to give you those. You have to be handed those fluxes. So we've got our carbons moving. Because it's summer, we're going to have more photosynthesis happening than respiration. So we see these two processes. There's our photosynthesis, there's our respiration. Here's our two carbon pools. So we've got our inorganic, or our atmosphere, carbon dioxide, and then we have our organic carbon, so like a forest. So we can see that this arrow is thicker because we have a lot more photosynthesis going on than cellular respiration. So let's go ahead and actually look at some fluxes. Let's look at some numbers that might work for fluxes. So let's say that this summer we have if we're talking about organic carbon, we have a positive flux of 250 pounds, and we have a negative flux of 150 pounds. So we can guess that our forest, because our positive flux is bigger than our negative flux, our forest is going to get heavier. If we go over here and if we look at our inorganic carbon, we can kind of guess the opposite. It's actually losing more carbon than it is gaining. The photosynthesis is happening at a greater rate, which means that we're going to pull carbon dioxide out of the atmosphere into organics, and then our respiration is not happening as fast. What that means is our inorganic carbon pool is going to have an overall negative flux because it's losing more carbon than it is gaining. So let's do some math here and let's figure out what is this actually going to look like if we were to graph that. Alright, so in the previous slide what you just saw was that our fluxes for the organic carbon were positive 250 for our positive flux and negative 150 for our negative flux. So let's think about what that means for our numbers. So our organic carbon is going to have positive 250 for its positive flux and negative 150 for its negative flux. And what that means, if I add up my fluxes, I don't get 0 like I did earlier in another example. I actually get positive 100. This is my net flux for right now. So what that means is that I'm starting at 400, and if I add 100 to that, that's going to give me 500. And so what that means is that for summer, I should have my new mass right here at 500. So that deals with our organic carbon. So let's think about our inorganic carbon. Your inorganic carbon has a different situation going on. It's starting at a much higher number. It's starting at 800. However, the fluxes are flip-flopped. So let's see how that affects our inorganic carbon. So in that example, you actually were losing 250 pounds of carbon, and you were actually gaining 150. So if I went ahead and added these up, I would actually get a net change of negative 100. And so my inorganic carbon is actually going to go, it was 800, it is now going to lose 100 pounds, so that it is actually 700. And that's because its net gain is the opposite of our organics. And then, of course, if we were to think about our total, well, we're going to start at 1200 and we're going to end at 1200. So that's going to stay the same. Let's do one more season, and then that will do it for this example. So now let's think about winter. So summer has already occurred. Now let's think about winter. In this example, our photosynthesis is going to go way down. We might have a little bit of photosynthesis going on, but it's going to go way, way down. And our cellular respiration is a lot higher. So I'm going to tell you, all right, we're going to have 20 pounds added by photosynthesis and 120 removed from the forest by cellular respiration. Let's go ahead and graph that. Okay, so what we end up with here is that we see that our inorganic carbon is actually going to have a gain of 120 and a loss of 20. So our net gain is going to be plus 100. And so we're going to see our inorganic carbon actually increase back to 800. And if we do the same thing for our organic carbon, we're going to see the opposite. We're going to see that there's actually a loss of 120 and a gain of 20. And what that means is that we're going to have a net change of negative 100. So we're going to actually see a loss that's going to go right back down to the 400 where it was. So really, you just have to do this step by step, and we can figure out how this is going to change season by season. So if you were confused, jump back, maybe rewind, watch the video again. I'll do 2 more examples in another video.